Today I will talk about our project. What is steering head? The steering head is a part of frame where the steering stem is located. The steering stem is a metal rod that links the upper and lower triple clamps, which holding the forks in place. The steering head bearings is to ensure that the front end of the vehicle steers smoothly and steadily. We chose the steering stem head as one of the design to be proposed because it seems challenging to us.
We also faced some few challenges during the cam machining. We also stuck several times during the process machining since we had to figure out which process was the best for each component in the design and what is the cutting speed and also the utilized for each tool. And we also have to configure the macro management. And the result is the design may not be identical to the one that we proposed, but we tried our best to make it as close as possible.
Steering stem head is one of the designs proposed that have been chosen by our lecturer, Mrs. Encik Zulkarnain. We use this photo as our reference. As you can see from this photo, 9 dimensions was provided. Thus, we have decided to create our own dimension that's suitable for this project. Moving on to the 3D modeling, we start from the very beginning, which is 2D sketching. We use multiple planes and then we deep extrude each of the sketches from each plane. This is our 3D modeling that we did by ourselves.
And I will present about our process blending in this project. So as you can see, this is our stock here, and we use 3 plan system here. We put our plan system at the corner here, the second one here, and the third one is here. And then we use this kind of tool to make all the process. And then for the part operation, first we make the facing, and we use the facing diameter 63, and then we make profile contouring to profile the outer stock to make the shape of the product. And then we use pocketing, and then another pocketing, and then we profile contouring. We profile the pole section so that we can have the pole, and then we profile another side of the pole and the circle here, and then we make a hole at the circle here to make pocket, and we make another pocket here to make hole, and another pocket here to make a hole. And then we profile here to make the shape of the circle, and then we use another pocket to make the process at the back here, and another pocket here to make a hole here. All of these we use the end mill diameter 10.
Assalamualaikum warahmatullahi wabarakatuh. My name is Fitri Dana. I'm in charge in machining process. So, firstly, we need to define our tool that we want to use. So, this is the list of the tool that we want to use. But for this operations process, we are just using face mill diameter 63, end mill diameter 10, conical mill diameter 25 with a 60 degree angle, a center drill, and also drill diameter 6 for this hole. So, other tool, we just try and error for the process, but we are just using this for 1, 2, 3, 4, and 5. Sorry. So, the first process is facing. Okay, we are using 2 parts high in the one-way machining. Tolerance 0.1 mm, radial to diameter ratio with a percentage of 2 diameter 40 and a path out for the issue maximum depth of cut 3 mm. 263 diameter is here. For the macro approach, we are using this point to a motion to a point and a motion perpendicular to a plane. For retracts also, and then written in a level retract, written in a level approach, written between level retracts, written between level approach. So let's start to simulate. So first, it will rapidly the rapid plane, and then it will start approaching toward the stalk, and it will cut the stalk, and then it will retract, and it will approach again. So let's see how it runs. See, it will out and also out like before. Okay, after facing, we are using annual diameter time for profile the first process. So for the profile, we use one way for 2 part style and time directions of cut, machine tolerance seen as a pacing 0.1, the type of contour is circular. And then for the step over, distance between part is 8 mm and number of part is 5. For the macro, we are using these ramping motions, the circular motions, and a motion to a perpendicular plane. Also a retract with the circular motions and a plane. Written in level retracts, we are using circular motions and axial motions and a horizontal motions. Same goes to a written in level approach, and also written in between level retracts and written between level approach. Let's see how it runs. Okay. As you can see, this is what means 1, 2, 3, 4, 5. This is a 5 times of part. It will run like this, and the distance between part is 8 mm. Let's see. Okay, after that, we are doing a pocketing for this area. Wait, let me hide the stock first. So we are doing a pocketing for this area, since as you can see from the side, it got a different level of island. So the same functioning tolerance 0.1 mm, radio 2 diameter mode, 2 diameter ratios, this 2 diameter. Percentage of the 2 diameter we are using 50%, and actual maximum depth of cut is 2 mm. For the macro approachings, we are using a ramping motions and a perpendicular to a plane, motion perpendicular to a plane, and a motion to a point. Retracts and return between level. We are using axial motions and a ramping with the angle 3 degrees. So let's see how it's. It will cut this area. And left this, and this as an island. Okay, for the next process is pocketing too. Let's see as a before. Let's see. This is for the second time. Okay, next. Profile contouring for this, because when we are doing a pocketing, it still got a little blur here. So for the profile, direction of cut is fine, machine tolerance 0.1 mm. And then the step over the first, distance between part is 5 mm and number of part is 1. Because we just want to profile this area. So this is profile, approaching, retracts, only. Trying to simulate. See, it will provide this area only. Okay, for the next step is providing this area. As you can see here, I did make a boundary over here because we want to provide this area only. If we didn't make this boundary, we cannot provide this area. So at this, or we did define our boundary over here. So it will provide through this boundary only. Let's see how it's works. See, it follows the boundary that we made before. Okay, for the next step is locating. I will profile this area only. After we make the pocket, we will need to profile. And then at the back, you see from here, I will make the pocket here, this area only. Okay, this for this area. Okay, next. Okay, as you can see here, this is a pocketing. For this hole, we need to use this plane system. That's why this for the part operation, we get a 3 part operations. For the part operation 2, for this area. Before we pocket, we need to make a boundary over here so that it will pocket through this area only. Okay, so the same goes to this part that we are using this plane system for the part operation 3. Okay. Okay, so back to the, so for this chamfer area, we are using multi-existent contouring with a 2 conical mean 10 to 25, angle 60. Distance with the part is 5, number of part is 1. So let's take first. This is already. This also ready. The whole tracks. Also. Here. Here we go, and so we'll make this chamfer with a 60 degree. Okay, next, the center drill. For this, for hole. We're using spot drilling process for the drill, for the center drill. Approach clearing 3 mm. With depth is 8 mm, jump distance 10 mm, and approach and retract will automatically on and start to stimulate. Okay, and then the last step is center drill. It's a drill ring. Sorry. with a drill 2-10-6. This is a drilling the hole process with a 3 mm okay, clearance. The drill initiates with this S3 because it will go through. Okay. And also approach and reduct the micro. Some distance times. Okay, I'll try to simulate. See? Okay. Sorry. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Ahmad Shazwan bin Abdul Maulud. I would like to overview discussion and result. Based on this experiment, we are planning to use aluminium as our workpiece. Besides that, we have learned how to organize the milling machine and understand the operation involved. We also know the purpose of the main part of this machine. Furthermore, we realized that the cutter diameter should be chosen in such a manner that it will not interfere with fixture and other components in the setup before running at the actual machine. We also learned about the process that are suitable for each type of part. This is our part. As we can see, for the facing process, we are using face mill 63 of the diameter. Then, as we can see, end mill, we use the diameter 10. On the design, we supposedly use 5-axis machining to make it easier, but for this experiment we are using 3-axis machining. That's why we add more plane system to machining the different parts of plane. This is a final result. From this final result, we can see we have the boundary at here. This profile process, we put boundary as in the photo above to make it easier to do profile process. Since the gap between elongated hole and circle are small, and the result shows that it's not fully profile since the use of tools are not suitable, which is end mill diameter 10 mm. So in this case, we found out the way to profile the small gap with a range the in and out of the cutting tool. Try to avoid repeated machine at the junction, otherwise obvious boundary traces will appear, and change the tool size with the size that can enter the small gap between the two holes. On this machining, on the top part, we need to add more plane system to cut the half circle on the elongated hole, because we are using 3-axis machining. Besides that, for the chamfering, we are using conical end mill 25 mm diameter and 60-degree angle, but we do not get the angle as in the 3D part because the angle for the 3D drawing are not same as the tool. That's all. Thank you.
It has been an opportunity for us to learn a lot about Catia software and also the job that it can assist with. We also been taught about the 3D modeling at the start of the semester by learning how to make small individual pieces. It has been moved to putting pieces together to create an assembly by properly attaching and restricting them. Then it is evolved into putting up a complete product or assembly in Katia simulation and analysis section. On several assemblies, we also practice doing a finite element analysis. Despite there are a few challenges in completing this assignment, we were very fortunate that we were able to complete the task set by the lecturer. And we were able to generate at least one workpiece that we developed. There were 21,220 programs. We also illegally utilized 5-axis machining and 3-axis machining as per mentioned in the discussion. Able to create the NC code. Lastly, we all agree that a lot of time, effort and planning went into this steering stem head as a group. Everything about our project from start to finish falls neatly inside the needed parameters.